Today we are going to be talking about the concept of mesh analysis. Mesh analysis, oh, why is my stylus not writing? There we go. Mesh analysis is very similar to nodal analysis, except that instead of writing multiple Kirchhoff's current law equations, we wind up writing multiple Kirchhoff's voltage law equations. So I'm going to introduce this concept to you very similarly to how I did it for nodal analysis last Thursday. We are going to develop a step-by-step procedure that will allow us to solve almost any circuit using this technique successfully. The reason why I say almost any circuit is because mesh analysis cannot be applied to three-dimensional circuits. So if we made like a cube of circuit components, mesh analysis would not work while nodal analysis would. There are going to be extraordinarily few cases where you'll ever see a circuit that can't be flattened out into a 2D shape. So for the intents and purposes of this class, you can use mesh analysis on practically everything, just like you can for nodal analysis. So I'm going to start by drawing a circuit. And this circuit is going to contain only voltage sources. And after we understand the basics, we'll include current sources and learn about super meshes, again, very similar to what we experienced with our nodal analysis last Thursday. So let's say that we have a 10-volt source here. Let's put a 9-ohm resistor here. Let's put a dependent voltage source here. Let's make this 2ix. We'll put a 4-ohm resistor down here. Put a 1-ohm resistor here. A 7-ohm resistor here. A 3-ohm resistor here. And then an 8-ohm resistor over here. I'm going to define my current Ix to be the current flowing from left to right through this 3-ohm resistor, like so. And now let's talk about the various steps for mesh analysis. So our first step is going to be for us to identify our meshes. So if you recall from our very first class meeting, a mesh is simply a loop that doesn't contain any smaller loops. So this particular circuit contains 3 meshes. So we're going to have this mesh that I'm outlining here in red. Then we're going to have this mesh in the top right in blue. And this mesh, which I will put in green, in the bottom right. Our second step, I apologize, my stylus is acting a little funny today, not as bad as it did that one day, so we'll get through this. In the second step here, we are going to label our mesh currents. So we have a choice to make here. So let me start by saying first what a mesh current is. So a mesh current is simply a current that flows around one of these meshes, okay? We can choose for our mesh currents to flow either in a clockwise direction or a counterclockwise direction. I, typically speaking, choose all my mesh currents to flow in a clockwise direction. This is not required. You could do all counterclockwise, or you could do some combination of clockwise and counterclockwise. But I truly believe that you will get the best results from this analysis procedure if you choose one particular direction for all of your mesh currents, excuse me, either clockwise or counterclockwise. So I'm going to choose clockwise, and I'm going to indicate that by drawing this little loop thing here. So this is just telling me what direction I assume this mesh current is flowing. I'm going to call this mesh current I1. I'm going to do the same thing here. Let's call this mesh current I2 and this mesh current I3. So what these mesh currents represent is the amount of current flowing through the individual branches, okay? So I'll label some of these currents. Let me use this purple color because I haven't used it yet. So like this current flowing from left to right through the 9 ohm resistor is the exact same thing as mesh current I1, because as mesh current I1 flows around its clockwise path, it will flow from left to right through the 9 ohm resistor. This current right here would be the same as negative our mesh current I3, because as I3 flows around its clockwise path, it will flow from top to bottom through the 8 ohm resistor, and I have chosen this current flowing from bottom to top. Since it's in the opposite direction as our mesh current, it is the negative of our mesh current. The last one that I want to talk about, let's do this one right here, is this current through our 4 ohm resistor. So this current would be expressed as I1 minus I3. It's expressed as I1 minus I3 because as I1 flows around its clockwise path, the portion that flows through the 4 ohm resistor is in the same direction. So it flows from, the portion of I1 flows from top to bottom, whereas when I3 flows through the 4 ohm resistor, it is going to flow from bottom to top. So the mesh current that is in the same direction as the arrow gets a positive sign, and the mesh current that is in the opposite direction of the arrow gets a minus sign, okay? So we're going to use these total currents flowing through our resistors expressed in terms of our mesh currents to write our Kirchhoff's voltage law equations when we get to that step. But I just wanted to talk about, talk very briefly about what our mesh currents actually mean. Okay, so these are our 2 setup steps. There is no reference or anything like that to use when you're applying mesh analysis. So our 3rd step is going to be one of those easy to forget steps. We are again going to express our controlling variables in terms of our mesh currents. So in this particular circuit, the current IX controls our current controlled voltage source, and IX is the current flowing from left to right through the 3 ohm resistor. As our mesh current I3 passes through the 3 ohm resistor, it is flowing in the same direction as indicated by the arrow for IX. So we're going to have positive I3. And the current I2 is flowing in the opposite direction as it flows through the 3 ohm resistor. So we're going to have Ix is equal to I3 minus I2. Just for the sake of argument here, let's talk about how we might define a voltage as a controlling variable. So let's say that we wanted the voltage drop across our 4 ohm resistor, and it was labeled as the quantity Vy. Okay. So using Ohm's law, we are going to have the total current flowing into the positive polarity terminal, which is simply I1 minus I3. My stylus is being funny. Times that 4 ohms of resistance, because V is equal to I times R. And we are practically always going to choose the current, the total current flowing into the positive polarity terminal, so that we won't get extra negative signs here. Okay. So we've now talked about how to express both currents and voltages as controlling variables in terms of our mesh currents. If any of you have any questions to this point, by all means, please ask. If not, we'll move along to writing our Kirchhoff's voltage law equations here in just a minute. All right, I'm not hearing any questions. So let's get to the KVL. So what we're going to do, if my stylus will write, step number 4 is we are going to write a KVL equation for each mesh. And we are going to follow that mesh current around its clockwise path. So I'm just going to write KVL equations here like I've written them at every other point in this class. I'm going to start from the bottom left-hand corner of my mesh, and then I'm just going to follow that mesh current or the mesh currents around that clockwise path until I get back to the same node. So starting at mesh 1, the first thing that we're going to see is the negative polarity terminal of the 10-volt source. So I'm going to have minus 10 volts. The next thing I see is the 9 ohm resistor. Since I want the voltage drop across the 9 ohm resistor, that's just going to look like 9 ohms times I1, right? So we can see up here that whenever a circuit element is on the perimeter or on the edge of the circuit, it's only going to have a single current flowing through it, okay? The next thing that we're going to see is our current controlled voltage source. We see the positive polarity terminal first. So that's going to be plus 2Ix. And then we see our 4 ohm resistor. So we're looking for the current flowing down. Effectively, if we're following I1 around its clockwise path, it should be having the positive sign, and any current in the opposite direction of I1 should have the negative sign. So the voltage drop across the 4 ohm resistor in this case is going to look like 4 ohms times I1 minus I3. We set this equal to 0. Now we're going to write our KVL equation around mesh 2. So starting at the bottom left-hand corner, the first thing I see is the negative polarity terminal for the voltage, excuse me, current controlled voltage source. That's going to look like a negative 2Ix. excuse me. Then I see the 1 ohm resistor. The only current flowing through the 1 ohm resistor is our mesh current I2. Then I see the 7 ohm resistor. The only current flowing through the 7 ohm resistor is our mesh current I2. And then we see our 3 ohm resistor. And I would like help from you guys in deciding what current is flowing through the 3 ohm resistor here.
I2 minus I3.
Absolutely correct. I2 minus I3. So once again, if we're following mesh current 2 around its clockwise path, it should get the positive sign, and any current in the opposite direction gets a negative sign. So absolutely perfect. Wonderful job. Now we'll write our KVL equation for mesh 3. So starting from the bottom left-hand corner, the first thing we see is our 4 ohm resistor. So that's going to look like 4 ohms. Now that we're following mesh current 3 around, we're going to have I3 minus I1. Then we are going to see our 3 ohm resistor. We're going to have I3 minus I2. And then lastly, I believe we have an 8 ohm resistor that only carries a current of I3, and we set this equal to 0. Okay. That's right. And so now the only thing left for us to do is solve this system. Right. So I'm going to do this as a 3x3 system where we know that IX is just I3 minus I2. So I'm going to make a note here. And I'm going to grab one of my multitude of calculators. Looks like it's going to be a TI for today. And talk you through how I'm setting up this system in my calculator. So when I'm looking at the first equation, the coefficient for I1 is going to be positive 9 plus 4. So 9 plus 4. My coefficient for I2 is going to be negative 2. Actually, let me do this. So here's my coefficient for I1. My coefficient for I2 is this guy right here, but it's going to be negative. That's it. My coefficient for I3 is going to be this guy right here, but it's going to be positive this time. So positive 2 minus 4. So 2 minus 4 looks like negative 2. And then my constant term is going to be positive 10 when I move it over to the other side. In my second equation, I don't see any I1s, so that coefficient is going to be 0. My coefficient for I2 is going to be negative 2, so it's going to look like positive 2 from here, 1 from here, 7 from here, and 3 from here. So 2 plus 1 plus 7 plus 3. My coefficient for I3, doing that in green, is going to be negative 2 and negative 3. And my constant term looks like it's going to be 0. For my third equation, my coefficient for I1 is going to be negative 4. That's it. My coefficient for I2 is going to be negative 3. And then my coefficient for I3 is going to be +4 + 3 + 8. And my constant term is 0. And solving this system of equations, what I find is that my mesh current I1 is equal to 50/61 amps. My mesh current I2 is equal to 50/549 amps. And my mesh current for I3 is equal to 130/549 amps. Assuming I entered everything correctly into my calculator, which I believe I did, but there's always opportunities for mistakes here, okay? So now we know all of our mesh currents, and then using simple relationships, we can figure out literally any other current in our circuit. For instance, IX is just I3 minus I2. So 50 minus 130 is, no, excuse me, 130 minus 50 is positive 80 over 549 amps. Once we know all of our currents, we can use Ohm's law to determine all of our voltages. And then once we know currents and voltages, we can obviously determine any power that we might be interested in. So just for the sake of arguments, let's find the power that is supplied by our dependent source, right? So the power supplied by our dependent source, P sub dependent, is going to be the voltage drop across our dependent source multiplied by the current flowing into the negative polarity terminal of our dependent source. Well, the voltage drop across our dependent source is simply twice IX because it's a 2IX current controlled voltage source. What is the current? Let me scroll up here. The total current seen flowing into the negative polarity terminal of our dependent voltage source. So just
I2 minus I1.
I2 minus I1, absolutely correct. I'm going to go ahead and label this really quickly so that it's obvious for everyone else. This is the current that we're looking for. As I2 passes through that voltage source, it's flowing from bottom to top. So that's why I2 gets a positive sign. When I1 flows through that voltage source, it's flowing from top to bottom. So it should get a minus sign. So that current I dependent is going to be I2 minus I1, exactly correct. So putting this in my calculator, I'm going to have 2 times I3 minus I2, which is just IX. So Z minus Y multiplied by Y minus X. And I get negative 0.212 and some change watts. So much like when we did nodal analysis, once we've finished our mesh analysis here, we are literally at most 1 to 2 steps away from knowing any other current, voltage, or power related quantity we could possibly be interested in. So this is, again, a very, very powerful circuit analysis tool to be utilized, okay? So do you guys want to work another example where you provide me feedback and effectively tell me what the relationships should be? Or do you want me to move along to what happens when we include current sources to mesh analysis.
Current sources.
Current.
Could we see a homework problem related to this? At least the start of one?
Sure, absolutely.
Okay.
So let me pull up the web work here really quickly. Are we talking? Well, actually, this is going to be lower-ish difficulty because it doesn't contain any current sources, but let's see what we can do. Not that including current sources really ups the difficulty level by any huge amount, but yeah.
But would that be homework set 7?
Yes, homework set 7. I'm looking at problem 1 right now.
But like nothing trivial, I don't know.
Yeah, no. I'm happy to work more example problems.
Okay.
Let's look at homework 7 problem 2, at least setting it up.
Okay.
No dependent sources, but it does look like it's going to have 5 meshes for us to deal with.
Yeah. So I guess like an assumption I would have, if it has 5 meshes, would that be 5 equations?
Yes.
Okay.
So 5 meshes means at least 5 equations. The reason why I say at least, the dependent source, we're also going to have a controlling variable relationship that's going to contribute an equation as well. So, all right. So this is homework number 7.2. We're just using my numbers. So we have a 25 ohm resistor across the top like so. And we're just going to set this up because I don't want to spend a lot of time doing MathCAD, although I'm willing to if you guys really want it. But I'd rather talk about what happens when we have current sources here in a minute. So 6.5 volts here. $40 ohm resistor. This is going to be a short circuit. This is a short circuit. $60 ohm resistor here. 4.5 volts. And then we have a 30 ohm resistor here. Two and a half volts. And a 120 ohm resistor here. And then our ultimate goal for this particular problem would be to solve for this current IX. Yep, actually, no, I was going to say I'm going to skip it, but since we're still learning it, I'm going to leave this step in. So that's 1. 2. 3. 4. And 5. Now I'm going to label my currents. So this is I1, I2, excuse me, I3, I4, and I5. So we've done steps 1 and 2. There are no dependent sources, so we have no controlling variable relationships to write. So we're off to the races with our Kirchhoff's voltage law relationship, okay? So let's start over here. KVL at mesh 1. Anybody care to tell me what this KVL relationship should look like?
$25 times I1
All right,
plus 40 times I1 minus I3
absolutely correct.
minus 6.5 volts.
Set that equal to 0, and we're done. Wonderful job. Somebody else tell me what's going on with mesh 2.
Would that be I2 times 60 ohms?
So that's going to be a part of it, but for consistency's sake, let's start at the bottom left-hand corner and work our way around our mesh, right? So if we start at the bottom left-hand corner, the first thing we see is a wire. The voltage drop across a wire is 0. So the first real thing we see is the positive polarity terminal of the 6.5 volt source, right?
Right.
So I'm going to start with 6.5 volts. Then we see another wire as we're coming down through that middle branch. And then we see our 60 ohm resistor, right? Now you had suggested that the current flowing through the 60 ohm resistor is I2, and that is part of it, but that's not the only current flowing through that 60 ohm resistor, right? I4 is going to flow
We lost you, Dr. Hartman.
both mesh 2 and mesh 4. Sorry, what was that?
We lost you. Right after you started to talk about I4, and then at least I lost you.
Yeah, the internet connection here in my office on campus sometimes is spotty, so I apologize for that.
Okay.
What I was saying is that the 60 ohm resistor is between meshes 2 and mesh 4. We are going to see that I2 and I4 will flow through that 60 ohm resistor.
Yeah. Okay.
So since I4 flows in the opposite direction of I2, we're going to have minus I4 here.
Okay.
So Christian, I'm going to call on you again. Tell me what's going on here with mesh 3. It's a similar situation, so this is an opportunity to redeem yourself, so to speak. Not that there was anything wrong with making a mistake.
Okay. All right. So let's see. So we would go through your V2 that 4.5, or starting at the bottom left, it would be 40 ohms times I3 minus I1.
Absolutely right.
And then since we're
Ooh,
entering,
what the heck happened there? Yeah, sorry. My screen moved on me really abruptly there. Sorry about that.
all good. And so since we're entering the negative terminal of the voltage source, it would be minus 4.5 volts
Absolutely right.
equals 0.
Mhm.
Cool.
Nailed it.
Sorry.
All right. Let's look at mesh 4.
Can I take it again? Unless someone else wants to. 34. Okay. All right.
I don't hear anybody speaking up, so you go for it.
Okay. All right. So this bottom left, so it would be 30 ohms times I4 plus 60 ohms times I4 minus I2,
Okay,
and then plus 2.5 volts equals 0.
absolutely right.
Okay, cool.
And then here, our last KVL expression is gonna be around mesh 5. Somebody else take a crack at this one if you don't mind.
Minus 2.5 volts
So negative
Plus-
2.5 volts, all right,
plus 4.5 volts
plus 4.5 volts, okay,
plus 120 ohms times I5.
120 ohms times I5 is equal to 0. And then we would solve this system of equations for those mesh currents, tying it all together at the end. How would I express this current IX in terms of those mesh currents? Which is what our ultimate goal in this problem would be.
I4 minus I5.
Absolutely right. So if you can put this system into your computer equation solver of choice, which I highly prefer MathCAD mainly because I know how to use it, you would be able to get the answer for this particular homework problem. All right, so it seems like you guys have a pretty good grasp on this thus far. So as usual, I'm going to be a jerk and try to mess things up by making it a little bit harder. So let me pull up another problem here. So we are now going to introduce current sources into our system. I'm going to have a short circuit here. This is going to be a 10 ohm resistor up top. I'm going to put a 3 ohm resistor here. We'll put a 5 amp source here. And it's going to be in series with a 2 ohm resistor. We're going to have a 4 ohm resistor over here. Here we have a 4-volt source. A 2IX volt source. A 5 ohm resistor here. Our current IX is the current flowing up. And then let's put a 6 amp source direction down over here. So much like we saw in nodal analysis, our setup here is going to be effectively unchanged. So steps 1 and 2 don't change at all. Step number 3, actually, let me do them. I guess that would be helpful. So that's one mesh. Another mesh. Another mesh. And let's do pink. 4th mesh. Now I'm going to label my mesh currents. So this is I1. This mesh will have I2. This mesh will have I3. This mesh will have I4. Okay, so there's steps 1 and 2. Because we have current sources, we're going to have a new first step in our actual analysis. So this is going to be our new step 3. We are going to write current relationship equations for each current source. So there are 2 current sources in our circuit. So that means we're going to come up with 2 of our equations right here. So the first one I'm going to write is for my 5 amp source. So the 5 amp source is in between mesh 1 and mesh 3. Since mesh current 3 is flowing in the same direction when it flows through that middle branch of the circuit, we're going to have positive I3, and I1 is flowing in the opposite direction as indicated by the 5 amp source. So I'm going to have minus I1. So 5 amps will be equal to I3 minus I1 because once again, I3 is in the same direction as the current source and I1 is in the opposite direction as the current source when those mesh currents flow around their clock. Help me out with what's going on for our 6 amp source.
Just equal to I4.
Absolutely correct. Just I4. Okay. All right. Now we write our controlling variable equations. So I'm just going to do express controlling variable dot dot dot. You guys know what we're supposed to be doing here. Our only controlling variable is the current IX. So what's that going to be in terms of our mesh currents?
Isn't that just 5 ohms times I4 minus I3?
So you're very close. The mistake you've made is including the 5 ohms. So Ohm's law tells us that V is equal to R times I. Right? So if you multiply that combination of currents times a resistance, you're giving me a voltage. If I just want the current, it's just I4 minus I3.
Oh, okay, I see. Gotcha.
Very, very common mistake. All right, so that's our only controlling variable. So now we're going to get into the Kirchhoff's voltage law portion. Okay, so the first thing that we're going to do here is we are going to write KVL equations for all super meshes, which means I need to explain what a super mesh is. Okay. So when we were doing nodal analysis, anytime we had a voltage source, a super mesh was formed between the 2 nodes that the voltage source was touching. Okay. For super meshes, there's a little bit more nuance here. Okay. So we are going to have a super mesh anytime a current source is touching two meshes, okay? So that means we're gonna have a super mesh around our 5 amp source, but we are not going to have a super mesh for our 6 amp source because our 6 amp source is only touching one mesh. So what we're gonna do here is we are going to make a new loop that is the smallest possible loop that avoids taking the voltage drop over that 5 amp source. So our new mesh here, our super mesh, is going to be this path that I'm outlining in purple. So we're going to just follow mesh 1 around until we hit the branch that contains the current source. Then we are going to avoid it by coming down into mesh 3. Follow it around. Now that we have avoided the current source, we catch back up to where we were, okay? So the goal here is to just not include the voltage drop across that current source, because there is no way for us to express the voltage drop across a current source in terms of our mesh currents. Okay, so I am going to write this equation out for you guys to give you, some context of how these things are written here. So this is going to be KVL at super mesh 1, 3. And I'm going to start here. Okay. So at this point in the circuit, I'm following I1. So we're going to have 10 ohms times I1. The next thing that I see is the 4 ohm resistor. And at this point, we're still following I1. So that's going to look like 4 ohms times I1 minus I4. We are now at this point in the circuit. And so we're going to start following I3 around its path. So we're going to see the 5 ohm resistor, and it's going to carry a current of I3 minus I4. Then we go along that bottom short circuit, and we see the negative polarity terminal of our dependent voltage source. So I believe that's negative 2 IX. Scroll up here. Yep. We're now at this point in the circuit. So the last thing that we're going to see is the 3 ohm resistor. And at this point, we're following I1 again. So that's going to look like 3 ohms times I1 minus I2. Set this equal to 0. Okay. So I want to mention something here because students ask me about this a lot for problems like this. That 2 ohm resistor that's shared between mesh 1 and mesh 3 did not show up in our equation. That's perfectly okay. Okay. It shouldn't, because we're trying to avoid that entire branch. Effectively, the reason that we don't need to include it is because the voltage drop across the 2 ohm resistor is effectively a known quantity. It has to be 10 volts because we know that there are 5 amps flowing through it. So it doesn't really provide us any new information about our unknown quantities. It only gives us known things. Okay. So it doesn't hurt us in any way, shape, or form to not include that 2 ohm resistor. All right, so now we are going to write KVL equations. for all remaining meshes. That do not contain current sources. So for us, that's just going to be mesh 2. So when we scroll up here, somebody tell me what our Kirchhoff's voltage law equation around mesh 2, what it should look like.
Would that be 4 volts times I2?
So let me stop you there.
Okay,
First thing is, since we're starting from the bottom left-hand corner, the first thing we see is a negative polarity terminal, so it would be negative 4 volts. The second issue is that if I have 4 volts times the current, that's power. Since I'm just adding up voltage drops because I'm doing Kirchhoff's voltage law, anytime I see a voltage source, it's just the voltage source.
mm,
Okay, so it'll be negative 4 volts. Then what comes next?
would it be the 3 ohms? Yeah, 3 ohms times I2 minus I1.
There you go. 3 ohms times I2 minus I1. Absolutely correct.
Okay.
All right. And what should our last term be?
2I.
Keep on going.
Okay, 2ix. It's current.
So 2ix, because that's a voltage source. There's a positive polarity terminal and a negative polarity terminal, and that's it.
Okay.
So anytime you have a voltage source, doesn't matter if it's a dependent voltage source or a independent voltage source, we just add the voltage drop of the voltage source and we are done.
Okay.
So Kirchhoff's voltage law is literally just us adding up all of the voltage drops around a closed path. So we want to make sure that we're dealing with voltages specifically. And just to reinforce things, this bit right here is a voltage because it is resistance times current. And as we know from Ohm's law, V is equal to I times R. So let's count our equations here. We have our 2 current relationship equations, 1 controlling variable equation. Then we have our KVL around supermesh 1 through 3 equation, or supermesh 1 and 3 equation. And then we have our KVL at mesh 2 equation. So that looks like 5 equations for 5 unknowns. So let me talk about something here really quickly, because this is absolutely enough equations for us to work with. We didn't write an equation for mesh 4, or did we?
I4 is just 6 amps.
Right. So this is our equation for I4, for mesh 4, okay? The reason that we can get away with not writing any Kirchhoff's voltage law relationship equation is because that current source lies on the perimeter or the edge of the circuit. So anytime we have a current source on the edge of the circuit like that, we're never going to write a Kirchhoff's voltage law equation for 2 reasons. A, it's entirely unnecessary because our current relationship equation gives us all the information that we would need. And B, we actually can't. If we were to try to write a KVL equation around that loop, we would wind up having to take the voltage drop over the current source, which we cannot express in terms of our mesh currents. Okay. So we have enough equations to solve this system. So using MathCAD or some other computer algebra tool, we would get the following results. So let me write down here. Step number 7, solve the system. And I get I1 is equal to 33 over 19. I2 was equal to 203 over 57. I3 was equal to 128 over 19. I4 was equal to 6 amps. And IX, which was I4 minus I3. Let me throw that in my calculator because I don't actually have it on this thing here. 6 minus 128 over 19 comes out to be negative 14 over 19. And from here, once again, we could solve for any voltage using Ohm's law or any current, or excuse me, or any power using voltage and current. All right, so let me find another homework problem really quickly to illustrate something that I want to talk about here from mesh analysis. So this is kind of a special case thing. You won't see it a whole heck of a lot. And the worst comes to worst, I'll just make up a problem if I need to.
While you look at that, what are some things we could look at to identify that we would need to use this method versus the previous method?
Okay, so that's a fantastic question. Generally speaking, either of them will work. So here is my simple guideline, I guess you could call it. When I'm analyzing a circuit, any circuit, the first thing that I do is I check to see if I can do it first using KCL, KVL, or Ohm's law, just the simplest methods possible, okay? If that seems out, then I look for current and voltage division relationships. If that's out, that's when I bring in nodal or mesh analysis. If I'm trying to decide between nodal and mesh analysis, there are really two things that I'm looking for, okay? So the first is, which is going to give me the smallest system of equations that I need to solve? Because I feel personally that the smaller the system that I have to solve, the less opportunity there is for me to make a mistake, okay? So for this particular circuit, there were 4 meshes, which means we're going to be dealing with, at a minimum, a 4 equation, 4 unknown system. How many nodes were there? Well, there's a node here at the, let me circle them. This is one node, this is a node, this is a node, this is a node, this is a node, and this down here at the bottom is a node. So that looks like 6 nodes. Since one of them would be reference, that means that I would have a 5 equation, 5 unknown system just based on the number of nodes that I'm solving for, not including the fact that there might or might not be dependent sources for me to deal with. So mesh is going to be the simpler system to solve here, right? At least in my mind, because it will give me a smaller system of equations to solve. If you're going to get the same number of equations to solve using nodal or mesh, then I look and see, well, if I'm solving for a voltage, I'm going to use nodal analysis because nodal analysis gives me voltages directly. And if I'm solving for currents, then I'm going to use mesh analysis because mesh analysis lets me solve for currents directly. So those are the criterion that I use to choose what type of analysis that I'm going to apply. Which one is going to be more simple? And then if they're both of the same complexity, if I'm solving for a voltage, I use Kirchhoff's current or nodal analysis. If I'm solving for a current, I use mesh analysis. Did that answer your question?
It does. Yes, that was perfect. Thank you.
Okay.
That,
Yes, I can't really find an example of what I'm looking for here, so I'm just going to make something up. So
one other
sorry, go
thing,
ahead.
just kind of somewhat related, for the exam, like my calculator can do a max of 3x3. Is that kind of what we should expect on the exam?
Absolutely correct. Yes.
Okay.
So now I want to be clear about this. There could be a fourth equation and you would have to do some amount of substitution. But what I mean by that specifically is like a circuit like this, or let me scroll up here actually. Something more in line with this one, where we wound up coming up with 4 equations, one of them for Ix, and then we had to substitute that relationship in. That's the level of complexity that you should expect for your exam.
Okay.
So there might be a fourth equation where you can do a simple substitution into it to get it down to a 3x3 equation. There will be nothing on your exam that requires you to do more than a 3x3 system because I cannot force you all to buy the only calculator capable of solving a 4x4 system. You should notice that on all the practice tests too. Everything that I have written, I make sure that you can solve it as a 3x3 system.
Okay.
All right. Way back down here. All right. So this is a situation that you're not going to see a ton, but it does happen. Okay? So let's say I'm going to do something fairly simple here because this is just to illustrate a point. Let's say that I have a 4 amp source here. An 8 ohm resistor. 2 amp source here. 5 ohm resistor here. 10 ohm resistor here. 3 ohm resistor here. And then a 6 amp source over here. So let me identify my meshes really quickly. There's 1. Two. 3. I've actually kind of shot myself in the foot here very slightly, so I might modify this thing. It'll still illustrate the point as is, but it's actually a little more simple than I had intended. Okay. There are no dependent sources, so we've, yeah, sorry, I'm jarbling things up here. Let me label my mesh currents. Like so. All right, so what should my current
You broke out on what should my current be, and then it broke out.
Okay, sorry about that. What should my current relationship equations for this circuit be?
Okay, so first would, I guess, like you said, I would determine if I needed to use mesh or nodal. Well, we're using mesh.
We're definitely using mesh. So I'm at step 3 of the mesh analysis procedure when we have current sources, right? So if I'm applying mesh analysis, I need to write a current relationship equation for every current source in my circuit, right? So how do I relate the 4 amps that's being supplied by this current source on the left to my mesh currents?
It's equal to I1.
Yeah.
I1.
Because it's not connected to anything else. The 4 amp at least.
Right, so the mesh current I1 is on, or excuse me, the 4 amp source is on the perimeter or the edge of the circuit. So it's only going to have one current flowing through it.
Yeah, okay.
So if the mesh current is flowing in the same direction, it's positive. If the mesh current is flowing in the opposite direction, it'll be negative. We'll see that in just a moment with I3. But let's look at the 2 amp source. Okay, so what's my current relationship here?
I1 minus I2.
I1 minus I2. And then finally, our 6 amp source over on the right.
Negative I3.
So let me ask you guys a question. Do we need to write a single Kirchhoff's voltage law equation for this circuit at all?
No.
No,
Oh,
not going to happen often, but effectively, this, like I said, this was a little bit more simple than I had intended. But whenever we have, well, let me explain what I was trying to get at here. This 2 amp current source is between mesh 2 and mesh 1, right? But mesh 1 is in a mesh that contains a current source on the edge of a circuit. So whenever we have a super mesh, right, because there's a current source that's on the interior here. So we're going to have a super mesh between meshes 1 and 2, but that super mesh also contains a current source on the edge. We're not going to write a KVL equation. We're only going to have those 2 current relationship equations, and that's all that's needed. Okay, so it doesn't happen a ton of the time, or a lot of the time, but it does happen every now and then. And as a matter of fact, your third problem from your in-class assignment for today is a good example of a super mesh that contains a perimeter current source to where you don't have to write the KVL equation. So, all right, so I talked for significantly less today than I did on Thursday. Do you guys want me to continue to work another or so, or do you want to be left to work your in-class assignment?